Hi everyone, and welcome to my talk. I'm David Bond, a geologist at the University of Hull, and I've worked on mass extinctions for the past 20 years, and I'm currently in northern Spain, first time away like most people, almost 2 years, and I'm just away at the moment collecting Devonian rocks in Asturias to try and get a better understanding of the Devonian mass extinction, which will feature briefly in this talk today. But I hope you're enjoying the Yorkshire Fossil Festival 2021, wherever you are. This is my beginner's guide to mass extinctions. So first things first, let's get this out of the way. Extinction viruses. Viruses, of course, in the news for obvious reasons at the moment, but viruses do not cause mass extinctions. I have been asked this a few times, but it's not in the interest of a virus to wipe out its host species, otherwise the virus can't persist. But also viruses tend to be limited to a small number of species. And as we'll see, a mass extinction is responsible for wiping out a great number of species. So that's out of the way, we can move on. Now then, what is extinction? These are passenger pigeons, a photograph on the left there, and an etching on the right there showing how numerous they once were in the skies over North America. They were once one of the most common birds in North American skies, but now you don't see them at all, apart from stuffed in museums. And that's because they were wiped out. Here's a little newspaper clipping from Texas in 1914, when the last passenger pigeon in captivity died. And when the last individual of a species dies, we know that as species extinction. And Darwin recognized this as well. The survival of the fittest sees that only individuals that survive long enough to reproduce are able to pass on their characteristics to their offspring. And this is how a population evolves and changes over time. But sometimes, unfortunately, something interferes in that and extinction happens. So in the case of the passenger pigeon, it was because they were wiped out through hunting. And here's a more iconic, more recent example of a recently lost species. This is Lonesome George. He was the last surviving Pinta Island tortoise, native only to the Galapagos Islands, and he sadly died on June the 24th, 2012. And with his loss, Pinta Island tortoise became entirely extinct. And the great majority of Pinta Island tortoises were lost to goats that were introduced to the islands a few hundred years ago. Anyway, that's a species extinction, but we need to know what is a mass extinction, which is the theme of this talk, of course. Now, it may surprise you to realize or hear that there is no formal definition for a mass extinction, but I like this one from Jack Sapkowski, who wrote this in one of his final papers in 1996. He was a great pioneer of extinction studies. And his definition is that a mass extinction is a substantial increase in the amount of extinction suffered by more than one geographically widespread. So that's something key. It has to be not just in one area, it has to be spread around the globe. Higher taxon. So if we think about Lynnean classification, we're talking about things towards the top of Linnaeus' tree during a relatively short interval of geological time. Now that's very subjective. Does that mean 10,000 years or a million years or 10 million years? And there is no real definition of what a short interval of geologic time actually is. So speaking of Linnaeus, here is his classification of life on Earth. At the bottom there, we have the species, and species belong to a genus. So in our case, Homo sapiens, Homo is the genus, sapiens is our species. But you can see in this example, for instance, the moss rose belongs to the plant kingdom if we go right to the top of Linnaeus' tree. It's actually been updated slightly since this, but we'll keep it as simple as possible. And so with a mass extinction, we might be wiping out multiple families or even possibly whole orders of life. So if we think about this as an example, we'll use some motor cars. And I've given you the Lynnean classification here on the left for a bunch of Fords. So in this example, our family is the Motorcaridae. The genus here is the Forda, and there are multiple species. There are 6 species belonging to genus Forda here: the Sierra, the Fiesta, the T, the Focus, the Capri, and the Transit. So we've got all of those alive or extant at time 1. And let's move on to time interval 2, after some kind of geological boundary perhaps, or some history of the motor car industry. We only have 3 remaining: the Fiesta, the Focus, and the Transit. And the Sierra, the T, and the Capri have all become extinct. So we have lost 50% of our species, but you see the Fords are still there, and so are the Motorcaridae. So the idea here is that you have to kill a lot of species before we can wipe out either a single genus and let alone a whole family. So, and actually, if we look at modern forests, we know that there are several new ones that have radiated into this vacant ecospace. There is no loss in diversity here. We have a bunch of new ones, so we have the same number of species at time 2 as time 1. No mass extinction. So here's Jack Sapkowski and Dave Raup. I mentioned Jack Sapkowski earlier. He worked together with Dave Raup in Chicago in the 1970s and 80s, and they were real extinction pioneers. They did a lot of database work, tracked the record of animal life, particularly in the oceans, through geological time. And this is one of their classic figures from 1982. We have on the left axis there the number of genera, marine genera, through time. On the bottom axis there, extending from the Cambrian. So you see the Cambrian explosion, the big increase there in the number of marine genera. And as we move across to the right, we move towards the present day, where we have the most diverse life on Earth, and that's simply because the fossil record gets poorer the further back in time you go. And you can see here there are 5 big extinctions where the numbers of genera decline very sharply, and these are known as the Big 5 mass extinctions, which was one of their terms that they coined in the early 80s. So these Big 5 mass extinctions have a league table, and you can see here this is the number, this is species level extinctions on the right. So the earliest of the Big 5 was the End Ordovician mass extinction, which wiped out 60% of species in the ocean, nothing really on land at this time. But at the top of our league table, the End Permian mass extinction, which we'll focus on in this talk, wiped out 96% of species in the oceans and on land. So this is an incredibly devastating episode for the planet, which completely reshaped life on Earth. And we'll come back to this extinction shortly. But there have also been extinctions periodically, but not regularly through Earth history in the Triassic, in the Cretaceous, and in the Devonian, which is the one that I am collecting rocks in Spain for right now. Now, we'll also think about the Anthropocene, which has been suggested to be a modern geological age characterized by human impacts on. So that would be the present day. And currently there is 0% species extinction, although of course we have had species become extinct in the past few hundred years. We'll look at this in more detail later on. If we think about these extinctions through geological time, the Big 5 there are plotted on this, this well-known spiral of geological time, which hopefully people are familiar with. You can find this all over, but it shows key episodes like the evolution of humans at the bottom there, in the most recent time, going all the way back to the formation of the solar system 4.6 billion years ago. And you can see that the big red splodges, those are our Big 5 extinctions, have all occurred in the past 500 million years or so, or 440 million years, but they're interspersed with some of these yellow thumb bolts. And these are what Tony Hallam, who was an extinction from the 1960s onwards, had a very long career. He wrote a little book called Mass Extinctions and Lesser Calamities, and these yellow thunderbolts would be those lesser calamities, so intervals where maybe 30 or 40% of species have become extinct. One thing that's important to take away here is that there's a big cluster of those red splodges and yellow thunderbolts there, and then nothing much happens after the early Jurassic until the one on the left there, which is the demise of the non-flying dinosaurs at 66 million years before present, and that's our most recent mass extinction. But of course, we are worried about this red flag flying here, representing a possible Anthropocene extinction, which we'll come back to shortly. So one question just to think about as we go through the talk is, are we living in a new geological age characterized by human-driven extinctions? And this is a big topic, the Anthropocene. It might eventually be formally defined as a geological age, and if so, we'll need a stratotype, a point in time and space to mark the base of this age. And this is suggested to be one possible marker, global marker for the start of the Anthropocene. This was the explosion of the first atomic bomb, which left a record of radioactive carbon in all soils and marine sediments, pretty much all over the world. So that's a really interesting big topic, but we don't have time to go into it today. What we do have time to do is look at some past mass extinctions. And of course, if extinction has happened before, which we know it has from the fossil record, then in theory, it could happen again. But what might it look like? We need to go back in time, so let's do that now. Not a very exciting slide here, but this is a ranking of mass extinctions by different people And it just goes to show that you can use statistics to come up with pretty much whatever answer that you like. So in some cases, for instance, the end ordovician is placed in second place, but it's way down in seventh place in terms of how bad that extinction was. But what's clear from everybody's metrics is that the end Permian mass extinction is number one. Whichever way you look at it, this is the greatest crisis in the history of life on Earth. So let's have a look at the end Permian mass extinction. 252 million years ago, and this was a time on Earth where really life was coming out of the frying pan and into the fire. And as you'll perhaps take away from that, this is a period of extreme global warming and intense heat all around the world. This is the Discovery Channel DVD from probably about 15 years ago now, and they titled it "The Day the Earth Nearly Died." And now we have no evidence to suggest that this extinction only took a day, and we certainly have no evidence to suggest that the planet was hit by a meteorite impact, but it does make for a good DVD box cover, and it gives you an idea of how ingrained we've become in thinking that mass extinctions must be caused by meteorites, where in fact only one extinction is associated with meteorites, and that's the one at the end of the Cretaceous. So this is the end Permian world. This is a plate tectonic reconstruction from Chris Scottese, who has a very nice website called the PaleoMap Project. You get these maps from there. And he's reconstructed the Earth in one big supercontinent called Pangaea, which is there, made up of other smaller individual continents. But at this time, you could have walked pretty much from the North Pole to the South Pole without getting your feet wet. So all of the world's land masses kind of stuck together in one big lump like that. And then there's a huge ocean called the Panthalassa Ocean on the left-hand side of the image there. And the other ocean is the one on the right, which is the Tethys Ocean, or sometimes known as the Paleotethys Ocean as well. So very different way of operating for the planet because of this tectonic configuration. Now, the great thing about being a geologist, as I said, I'm in Spain at the moment, first travel for 2 years. But before the pandemic, I was able to go to lots of interesting places because we have to go to where the rocks are from the time period that we're trying to understand and investigate. So we had to go to lovely places like Bolzano in northern Italy. This is being filmed for Hungarian television. So it's a Permian-Triassic section in the Book Mountains. Go to places like Tibet, Spitsbergen up in the Arctic, Japan, which has a great record of the deep sea floor out of Panthalassa. Places like Turkey. At the other end of the temperature scale, there's Ellesmere Island up in Arctic Canada. Greenland, Idaho, intriguing, and all four corners of the world have interesting and valuable records of this end Permian mass extinction. So as a geologist, you get to travel to these places if you're lucky enough, and work as part of big teams to try and understand how these extinctions actually worked. And from all these places, we know about the victims on land, and this is a fossil festival, so I'm obliged to show a few fossily pictures or reconstructions. These are the paraiosaurs, the cheek lizards. So this is before the dinosaurs evolved, but these are the largest herbivorous Permian reptiles wandering around. And here we have the top Permian therapsids. So these are the meat eaters, the gorgonopsids. Both of these were wiped out during the end Permian extinction, as were these trees called Glossopteris, where it takes its name from the town of Glossop. But these were super abundant trees around the margins of Pangaea and Gondwana in the south in particular, that formed the majority of the world's coal. So we associate our coal in the UK with the Carboniferous, but actually a lot of the global coal formed around the edges of that supercontinent from this tree in the Permian. It was the only known mass extinction of insects as well. So insects have a very long fossil record and they're almost entirely indestructible. But the fact that they suffered mass extinction at this level shows you how bad conditions must have got for life. Now in the oceans, it's a story of almost entire destruction. So I've put up some pictures of various things that suffered either total or near total extinction at this level. The goniatites, crinoids, trilobites, it's their last hurrah. Brachiopods survived, but were severely depleted. Rugose and tabulate corals all disappear, so today's corals are completely different to those groups. Radiolarians and bivalves, for instance. So it affected almost all marine life, and as many as 96% of species globally in the oceans became extinct at this level. So how fast was this greatest of all catastrophes? How long did it take? Now this slide is 8 years old, and the dating here suggests that there are 2 steps of mass extinction. So the vertical dark grey lines that you see are the ranges in time of individual species, in this case microfossils called foraminifera. So lots of species here. And when that line terminates, that's when that species disappears from the fossil record. So this paper from Song et al. In 2013 suggested that there were 2 main pulses of mass extinction separated by about 180,000 years. Now the dating is done using geochemistry, usually uranium and lead dating on ash beds, in this case in South China. So that's 180,000 years. That's quite a long time, perhaps. So let's have a look at more recent dating. And here's a PopSci article based on a scientific paper that came out shortly after this paper, with more refined dating that suggests the Permian mass extinction perhaps only took 60,000 years. So the time scales for these extinctions tends to get shorter and shorter and shorter as the dating techniques get better and better. So what was the planet like at this time? How nasty did it get? And this is from Sun et al.'s 2012 paper in Science about lethally hot temperatures during the early Triassic. And what they recognized was that the fossil record of tetrapods on land, which are marked there in kind of beigey color, and the record of fish and sharks in the ocean, they all move out of the tropics. Everything has to escape to the higher latitudes, which suggests that the climate was warming and the planet was warming significantly, and that the tropical latitudes became really inhospitable. And they supported that with carbon isotope and oxygen isotope records, which showed that extreme warming may have caused this largest ever extinction. And their data actually suggests that the tropical sea temperatures got up to about 45 degrees C at this time, which is hotter than a hot shower. So your shower valve at home is probably set to about 38. So if you can imagine turning that up to 45, it really feels quite unpleasantly hot, and it's very difficult for most life to live in such conditions. So global warming, as we know, is linked to increased carbon dioxide. So do we have a record of CO2 increasing across this time interval? Yes, we do. We've seen extreme global warming before, as this article suggests, and we know, of course, that we're starting to see warming at the moment as well. And we'll come back to that shortly and compare the Permian to the present day. But as well as global warming and carbon dioxide, there were lots of other nasties around. If we look at the geochemistry record of the oceans, it suggests that there may have become lower in pH. So this is ocean acidification, which is a very hot topic at the moment. But there's also evidence for toxic metals in the ocean. So ocean acidification perhaps drove Earth's largest mass extinction. Ocean of acid blamed for Earth's great dying. And here we have toxic metal mercury may have caused the Permian mass extinction. So lots of other nasty stuff going on. And then there's also evidence for acid rain on land associated with ozone loss, so a big hole in the ozone layer. And that, of course, isn't good for anything living on land. And this is a result of the interaction of volcanic gases like sulfur dioxide with the atmosphere. So here we have a rather intriguing headline: vinegar-like acid rain may have fallen during Earth's worst extinction. And vanilla-flavored rocks. So there is evidence that fossilized soils have a particular compound, vanillin, in them, which gives vanilla its characteristic aroma. But this is a byproduct of them being subjected to acid rain. So more evidence building that the planet is becoming uninhabitable at this time. And of course, the loss of ozone in the atmosphere enhances ultraviolet B radiation, and that's very damaging to plants and trees living. It causes mutations in their pollen and spores, which can lead to them being unable to grow, reproduce. There are some slightly odd claims that there was a deadly ice age, so we have lots of evidence for warming, but here's a paper in Scientific Reports that suggests that there was a short-lived ice age. I don't really go in for this theory, mainly because the ice age is supposedly so short-lived that you can't actually detect it in the rock record. So you do get all sorts of weird and wonderful hypotheses, as you do for every mass extinction, but you have to take some of them with a big pinch of salt. So what is the culprit for all of this terrible things that are happening to the Earth in the end of the Permian? It's up here in northern Siberia. It's about the last place you could hide this much igneous rock, and it's called the Siberian Traps. It's 6 million cubic kilometres of lava, and it was all put there in a relatively short period of time, although we're still trying to get to grips with the dating and work out just how quickly all this lava erupted. To put that into perspective, this being the Yorkshire Fossil Festival, here is a map of Yorkshire from British Railways, and you might be able to locate yourself on there. But you know how big Yorkshire is. It's a huge area. It can take hours to drive from one corner to another. But the Siberian traps would have covered the whole of that area of Yorkshire in a pile of lava more than 500 kilometres high. So it's an enormous amount of volcanic rocks. And with volcanic rocks comes volcanic gases, which we think are responsible for all of the nastiness that's happening on the planet at this time. Speaking of volcanic gases, here we have a CO2 estimate for what this volcanic eruption or these volcanic eruptions would have released. And we'll come back to this, but remember this number. The Siberian traps probably released about 30,000 gigatons of CO2. Now, for perspective, that's about 10 times the amount of CO2 in today's atmosphere. So we have about 3,000 gigatons of CO2 in the modern atmosphere. Here's just a couple of maps just to give you an idea of the size of the Siberian traps. So the coloured things here in yellow and green and whatever, just different areas where the Siberian traps actually outcrop on land. And in the bottom corner, you have Lake Baikal, the world's largest lake there. So it gives you an idea of just the huge area of Siberia that these rocks cover. You can compare them to other examples of what we call large igneous provinces, which the Siberian traps is one. And you can see it's one of the biggest large igneous provinces of all time. There are lots of other ones on here that are associated with extinctions, and many that have no association with extinctions at all. So the Deccan Traps, which is in India, which you can see there as a splodge on the map of India, that's had something to do with the demise of the dinosaurs, but had interactions with, of course, the meteorite impact at that time as well. Now, coal, the Siberian traps erupted through a big coal basin. In fact, that was one of the reasons why they were discovered, because of exploration in Russia for coal, and they may have set fire to the coals in the Siberian traps. The Siberian traps, when they erupted through the coals may have caught fire, giving us increased fossil fuel burning. So there are papers here. We can see that we find evidence for coal burning from the ash and the char right around the world. So this is summarised by these little papers that I put in here: catastrophic dispersion of coal fly ash into the oceans in the latest Permian extinction. So we have plenty of evidence that there's an additional component of CO2 release, not only from what's coming out of the volcanic eruptions, but also from the burning of the coals that they erupted through. Okay, so with all that in mind, we're going to move on to more modern things in a moment. But here is a Permian-Triassic extinction scenario. Now, I'm not going to go through this in detail, but you can find this on the internet. It's a drawing that I put together, modified from one that Paul Wignall put together several years ago. But we have a cascade of things happening as a result of the eruptions of the Siberian traps. So the emissions of volcanic gases, like sulfur dioxide, carbon dioxide, that lead to various things like acid rain and global warming in the case of CO2. That then have knock-on effects such as ocean anoxia, which is where the oceans warm up and the amount of oxygen that they contain decreases, ocean acidification, ozone depletion, etc. And there's a very complex interplay between all of these, but ultimately you get from the Siberian traps eruptions at the top to a terrestrial and a marine mass extinction at the bottom. And there's plenty of this on the internet if you wish to read more about it. Now, after this extinction, and after every extinction, we have gaps in various records. So it wiped out Dasopteris, so we have a coal gap in the early Triassic. We have reef gaps because all corals have been wiped out, and various other gaps. And I like this little painting here. This is from Lost Worlds by the American artist William Stout. It's a series of paintings released as cards, and this is Lystrasaurus, one of the enigmatic survivors, tetrapod on land looking out over a barren Antarctica. It's not really clear why Lystrasaurus survived, but I feel sorry for this particular Lystrasaurus. Must be a very lonely place, looking out over the wastelands of Antarctica with very little to eat. But after 20 million years or so, the planet changed. It went from this very hot, arid environment, and it suddenly started raining in this intriguing event known as the Carnian pluvial event. It started raining in the Carnian stage of the Triassic, and suddenly the Earth starts to green up again. It took a long time, but it starts to bounce back. And this is where we see Eoraptor, supposedly the earliest dinosaur, evolve in the aftermath of the extinction into the available and vacant ecospace. And in fact, new things always evolve into vacant ecological niches. We wiped the slate clean with the Permian extinction, and then eventually the environment becomes hospitable and habitable there again, and things start to spring up and evolve into those gaps. It can take millions of years, and eventually, if we fast forward another 100 million years after the end Permian, we see things like Archaeopteryx evolving from the first dinosaurs approximately 150 million years ago. And then, of course, if we go back to 66 million years ago, we wipe out the non-flying dinosaurs. We have this terrible mixture of a huge meteorite impact and huge volcanic eruptions in the Deccan Traps in India. And together they wipe out many species in Earth's most recent mass extinction. But if it hadn't been for that, we might not be here today, who can possibly say? But it was only after the extinction of the dinosaurs that birds and mammals really started to take over the Earth. So without that meteorite hitting, Earth might look very different today. So, final part of the talk, should we be worried today? So let's have a look at some of the things that hit Permian Earth and have a think about whether they are a cause of concern in the modern. So we know that the Permian Earth was really very severely affected by global warming, which causes thermal stress to organisms. Marine anoxia, this is a result of global warming. So this is where you starve the oceans of oxygen. I usually make an analogy with a cold bottle of Coke, but we could think of a cold pint of beer. Might be nice right now. It stays nice and fizzy for as long as it remains cold. But the carbon dioxide, Coke or beer, will soon start to be released out of the liquid as it warms up. And that's because warm liquids hold less gas. And in the case of oxygen, that escapes, or the oceans as they become warmer can't contain as much oxygen. And without oxygen, most things die. So marine anoxia is a really potent extinction driver. Ocean acidification, as you increase CO2 in the atmosphere, you decrease the pH of the oceans. So a big problem in the Permian, potentially, although difficult to prove, and appearing to be a problem today for things like corals and other things that carbonate to build their skeletons. And as I mentioned, ozone damage and UVB radiation, within my lifetime, this has been an issue, of course, big holes in the ozone layer, still do in places. So we know about the problems that causes. As I said, must have been a big problem for life on land, at least in the Permian, as was acid rain, and possibly toxic metal poisoning, and possibly darkness and photosynthetic shutdown. So as you put ash and sulfur dioxide out of a volcano and into the atmosphere, they can actually block out the sunlight for several years. So all sorts of things that affected Permian Earth, many of which may be affecting our modern planet as well. So has Earth's sixth mass extinction already arrived? Now, I like the slide. It's now exactly 10 years old. It appeared in Nature in 2011 from Tony Barnowski and his group in America. What this shows is the extinction magnitude along the bottom there, with the big 5 in the bottom right corner. And then it looks at, here we are with, in white, percent of species extinct in the past 500 years. So for amphibians, for instance, 1% of them have gone in the past 500 years. The black numbers there are estimated to be at risk of extinction. So here with the scleractinian corals, 27% of those considered to be at risk of extinction. Some of these numbers are quite big, and that's because not many of them have been assessed for their extinction risks, such as the gastropods. So 56% of gastropods that have been assessed are considered to be at risk of extinction, but less than 3% of the total species have been assessed. So again, take these numbers with a pinch of salt. But some of these numbers, worryingly, are approaching that threshold there, which marks the big 5 mass extinctions. So how close are we to this sort of thing happening again? How close are we to an end Permian-style catastrophe? As I mentioned earlier, there's about 3,000 gigatons of CO2 in our modern atmosphere. And if we go back a few slides, where we looked at the estimated CO2 release from the Siberian traps, the Permian killer, it was about 10 times that mass at 30,000 gigatons. So what we need to do, although I'm not suggesting we do, but if we're to seriously create an Permian-style atmosphere and therefore a potential extinction catastrophe, we need to multiply the amount of CO2 in our modern atmosphere by tenfold. So the traps emitted 10 times the mass of CO2 in today's atmosphere. Let's look at this. This is the Keeling Curve, the most recent one I could find. So this is from just over a week ago. And this is the amount of CO2, the concentration in parts per million, as measured at the Mauna Loa Observatory in Hawaii, the Scripps Oceanography Institute. And you can see this is the last 60 years or so, back to the late 1950s. So if we take 50 years as our time frame, we look at 1971, there were 325 parts per million CO2 in the atmosphere. Now, or last week, it was 412 parts per million. So this is rising really quite rapidly over the past few decades. So let's do some simple maths here. Well, not simple for me, but hopefully straightforward enough to follow. In 50 years, carbon dioxide has increased by 87 ppm. On average, that's 1.74 ppm per year. So if we're multiplying the amount of CO2 in our atmosphere by tenfold, and to get towards our end Permian-style catastrophe, how long would it take at current rates to get to tenfold the present, 4120 ppm? It would take another 3,708 ppm to get to that sort of concentration, which would take 31.034 years, just over 2,000 years at current rates of emissions. So if we add that to our current date, it would mean that a then Permian-style catastrophe could strike in early 4152. Geologically speaking, that's in the blink of an eye. Or it could even be worse if we consider that current anthropogenic CO2 emissions, which are at an all-time high, 43 gigatons per year. So if we're to get to something like adding 30,000 gigatons of CO2, which is the amount that the Siberian traps actually put into the atmosphere, at current rates, it's going to take less than 700 years to release the same mass of CO2 as the entire Siberian traps released in the Permian. So really, really stark and worrying numbers here. This would give us an E-day, an extinction day, perhaps as soon, I've written it twice there, as 2718. But is this going to happen? Last couple of slides now, just to put some perspective on this. This is a sustainable energy transition path, showing how our reliance on traditional fossil fuels will be phased out in the next 20 to 30 years and be replaced by a much more varied energy mix, as they like to call it, made up of far more renewable sources and also some nuclear energy there, but things like geothermal, wind, photovoltaics, or solar power coming in there to make up the bulk of our energy mix. So if we're not going to be burning fossil fuels at the current rate much beyond this century, then perhaps that extinction date is not going to come. But also I think the final takeaway point here is that if we go back right to the start and our spiral of extinctions, we notice that apart from when the Earth was hit by a massive meteorite, there hasn't been any significant extinction crisis. And this is quite possibly because this was the time of Pangaea. When most of these crises were happening, the Earth was configured in a very different way to the present. And since Pangaea broke up in the Jurassic, or finally broke up in the Jurassic and became much more like its modern layout of continents, there hasn't been a mass extinction. So perhaps Pangaea was really bad for life on Earth, because it perhaps made ocean currents circulate very differently, for instance, but perhaps not having a supercontinent is much better for life on Earth. So many unknowns, and I will take questions, but I can't because I'm in Spain and it's 2 days ago. But there's lots of reading available on the internet if you want to get into this topic in more detail, including several freely accessible papers on mass extinctions in general. But I will leave you with a nice cartoon that I found with a spaceship flying away, thinking that we're idiots, and the skeleton here holding the United Nations report on global warming that clearly was not taken heed of. So thanks for listening to the talk. Hopefully Liam has been able to play this successfully, otherwise you won't be hearing it now. But yes, I hope you enjoyed the rest of the Fossil Festival. Thanks and goodbye.
So thank you very much, Virtual Dave. Obviously very sorry that we can't get Dave to appear in person for questions. As I said in the chat, if you do have questions or comments, I'm happy for you to post them in the chat. And I know somebody already has has done. In some cases, I might be able to answer them. I know Dave fairly well, and we've worked together in paleontology at the University of Hull. So there may be things I can answer, but equally, if you have questions that I can't answer, then you're very welcome to email yorksfossilfest@gmail.com, or indeed Dave directly. He has said he's happy to take questions via email. You go to the d.bond@hull.ac.uk. He will, well, when he's back from his fieldwork, he will probably respond as quickly as he can on that front. But yes, I think you'll see that hopefully you've seen that there's a lot of very useful and sometimes rather sobering information to be gathered from the fossil record to better understand what we may be facing, albeit what we're facing is a rather unique situation compared with previous mass extinctions. Okay, so yes, I hope you enjoyed that. I say what we will do is to make the talk available online. The Fossil Festival will come back in 2022 to Scarborough on the weekend of the 16th to the 18th of September. So if you are interested in planning well ahead, we hope very much to be significantly more in person than we have been able to be this year, but we also plan to have more online events to enable people to partake even from a distance. So thank you very much for signing up, and hopefully you found Dave's talk interesting, illuminating, and as Dave has said, there's plenty of stuff out there that you can explore further. Hope you have an enjoyable weekend.